I think that my main job is a structural engineer, not specifically thermal design of buildings or anything like that, but my passion is historic buildings. So this talk's going to be a little bit about historic buildings and then tying in some the thermal aspects of those. So let's start. If you've not, I live in Queenstown, basically in New Zealand. It's very nice there. I quite enjoy living there, and my house is just about there. So it's a good spot. It's a good view. So that's where I'm at the moment. But as Peter was saying, I started my academic life, I suppose, with a PhD in earth buildings, and I just basically bummed around the world looking at buildings. It was 10 years ago now, at least. So I think at that time there was a lot less understanding of what was really going on. From an engineering point of view, really. I think there were lots of ideas and lots of concepts, and I used that as a stepping stone, really. Go and look at some old buildings. Specifically, I looked at earth buildings that were damaged and falling down to understand how they failed. And this one it was built in 967 in Spain, and it's a castle, and it's got a graveyard on the inside. It's an amazing place. I came back from that and then went right down the other end of the scale. So we did scanning electron microscopes and lots of maths and lots of experiments, basically to do with the curvature of the meniscus of water between two soil particles, and the attractive force between those particles depends on the curvature of that, which depends on the relative humidity of the surrounding air. So we looked at the strength of earth buildings in relation to relative humidity, which was quite interesting if you enjoy that sort of thing. I then got a proper job designing, as a structural engineer, designing some earth buildings. And I think one thing that we can definitely say is a lot of the buildings get beautiful photographs taken of them. This one here is a wedding venue, and so amazingly, every single photograph of this building is, a wedding picture. So that's fantastic. So designed a couple of earth buildings as well. So that's good. And then I live in New Zealand, which is a little bit earthquake prone. I'm good at mud bricks and earth buildings, that sort of thing. So I went to Nepal following their earthquakes as part of the New Zealand team for that, and we did an awful lot of teaching of Nepali engineers about analysis of earth buildings and assessments, and carried out a few ourselves. And this is that is a mud brick to mud mortar interface shear test, basically. So if you know how strong the bond between the brick and the mortar is, then you can run that up and assess how strong the wall and how strong the building is in an earthquake. And this is a little method for doing it. So that's me doing that. Right. But less about me, let's talk about what I'm here to talk about. So I'm going to talk about thermal design of historic earth buildings. As Peter said, it's going to be not super technical, but just I'm going to run through the drivers, which I think most people know. A couple of disclaimers in there because it's not my direct field of expertise. Some of the methods that you can pick up from historic earth buildings, and then we'll conclude and see if you agree with what I think. So, thermal comfort. I think we heard quite a lot this morning about thermal comfort. So here's the standard temperature, and that's the water content of the air graph. And so there's a temperature within which people are comfortable, and there's a humidity range within which people are comfortable. And it's just a little bit more complicated than if you increase the water. You reduce the humidity. If you increase the water content in the air, you don't get a corresponding straight line increase in humidity because it changes the temperature because of latent heat of evaporation and all those things like that. But broadly speaking, you want to be in this zone here on this temperature water content graph, and if you're too far, you're too hot, too cold, too humid or too dry. So there's definitely a zone within which I think it's fairly well accepted. You want to be somewhere within this zone, and I think from this morning's discussions we need to work out whether that temperature is 15 degrees up to 35 degrees or whether it's a tighter band basically of temperature, and the same really with relative humidity. And what this doesn't pick up is airflow, clothing. I presume this works well if everyone's naked, but we're not all like that all of the time. And again, incident solar radiation is a function of clothing, but clothing also does keep the heat in as well. So that's a bit, that's a bit of a driver. The other thing really I'd like to talk about is expense in its most general sense. In that this is my wood pile. At my house, that's expensive to buy, it's expensive to cart around. Historic buildings, they had it, and historically, people had, they had exactly the same drivers as we do in terms of expense. It is expensive to gather fuel and to cart it around to burn it and do things. But it's possible. So active heating in terms of fuel is possible. Active cooling is a little bit more difficult because there's the refrigeration cycle, which heat pumps and AC units work on. That wasn't invented. So historically, active cooling was more difficult. And so what happened was historic buildings are sort of designed to limit the expense. They're designed to not really require loads and loads of fuel to heat them, or lots and lots of cooling. So sort of by definition, historic buildings they're acting in a more free-running way rather than the active cooling and heating that was talked about earlier. So, and the other thing I want to talk about is lifestyle. We don't really want to be transplanting, certainly for me, Northern European lifestyle straight onto a different climate. This is Sweden. I worked in Sweden for a little while. This is midnight on the Arctic Circle, and it's not dark. And so what happens in Sweden is everyone goes on holiday through the summer, and no work gets done, no one's in their house, everyone's outside. So no one really cares in Sweden if the houses are too hot right in the middle of summer, because that's when you're outside doing your stuff. But in Sweden, the houses in winter do need to be warm. So there's a lifestyle, and the Swedish and the Nordic lifestyles have developed around that. And if you move the Swedish house to somewhere else, it wouldn't work. And the same I've found in Spain. Obviously, the siestas and European countries, some southern European countries, the siesta, it's the same sort of thing, but in reverse. The middle of the day, too hot. Don't be working. Be in your cool place. So that's that one. So disclaimers, right? Generally speaking, I'm going to talk about earth buildings, but the principles apply to every other sort of building as well. But obviously, this being an earth building conference, then we want to talk about the earth buildings. The focus of my research was broadly monumental buildings, World Heritage sites, and big buildings. Now, their purpose is not necessarily thermal comfort. Whereas vernacular buildings, their purpose broadly is thermal comfort, and they're more usual. As an example of that, I've got Durham Cathedral. It's massive. So Durham's where I did my PhD. It's a very nice city in the north of England. It's massive. I don't know what it would get on a rating, a thermal assessment score, but that's not its purpose. So, and a lot of monumental earth buildings may fall into that category. I'm also really looking at thriving earth building locations. So in my experience, there's lots of earth buildings which are not necessarily built in the right location. And certainly if I look historically, there was a big, let's say in England's a good example, in the 1930s there were a lot of there were some test rammed earth buildings built, and that didn't go so well. So I don't think we should really be using those as, as good examples. So what I'd like to pick on is the places where earth building has either developed itself independently or has taken itself and run. So here is a good example. Western Australia is a good example. Earth building, it works there. Fantastic. We're good. And the other thing is historical decisions are not fully understood. So I think that people do things because they work, and the reasoning they have for that may not necessarily be correct. And so we're coming along now, and I think that's what a lot of my work has been doing. And I think as an example of that from a structural engineer's point of view, the columns inside Durham Cathedral are the same circumference as they are height. That's fabulous. That worked. That was the rule. But none of the people building that knew why. And I think that if we look at a lot of building design, certainly from a thermal point of view, it probably works, that's great. But what I would like to do is get in there and understand why it works and how it works. It's going to be quite pretty picture and qualitative. If you don't know, that's the partial differential equation for heat flow through a wall. If you solve that, this is basically the basis of all the software, but I'm not going to talk about any equations. And it's not exhaustive. I don't think I'll cover everything here, but it's a good start. So, right, so onto it. So I'm going to talk about shade, wall thickness, living arrangements, which are really a function of the building design only, and then evaporative cooling, wind catcher, stack effect. The simple things that you find in lots of buildings that I think we should just steal and use. This is Tatooine, which was filmed at this place in Morocco, and it's from an earth building point of view. This is definitely earth building. It's just building down in earth rather than building up in earth. But it's just the simplest example I could find of making your building which works with shade. There's nothing else going on there. You've got the thermal mass, I suppose, from the surrounding earth, and you've got shade inside in the courtyard. So very simple, but that's the sort of the number one bottom end. We can do that, and that's reducing incident solar onto you. It's cooling it. It has other effects, but simply it's shade. So, and then you find that repeated in other historic buildings. So this is Morocco, and they build very tall there. And from a structural engineering point of view, building tall is really quite difficult and expensive. You don't really need to build that tall from a defensive point of view, and so my sort of theory on that is that building tall is to get the shade on the inside. The courtyard to wall size is defined basically, and so that's what happens in a lot of Casbahs in Morocco. Calls that central courtyard. This is the Hakka Toulouse in Xiamen in China. Similar principle, but they've got a much larger internal courtyard. So similar sorts of climate there, but there the shade is sort of provided by the body of the building rather than the small courtyard that's always shaded. And the best way to do that, you find in lots of North African, Middle Eastern cities, is dense living. And so the courtyard, the streets within the Medinas here are all shaded, and you're inside most of the time. And that, to my mind, that's an expense thing. That right? Well, I'll just use the shade from my neighbour. And it's those sorts of principles. Is dense living, the way forward? So the living spaces are shaded, and the streets are shaded. And that's not a modern thing. This is just my historic thing coming through. So this is the Valley of the Kings. This is the worker accommodation for the pyramid building, which was excavated by someone at the University of Manchester in the 1870s. And just as a little aside, that's a mud brick mould that was dug out in Egypt, and so the methods for building mud bricks haven't changed very much recently. But we can see exactly the same principles there of very dense living, tight streets. There's no real requirement for them to be that tight. It's obviously done for a reason. There's no defence issues there, so I presume this is a thermal comfort setup. So, and just jumping across to North America, this is Taos Pueblo in New Mexico. Similar, but not the same. But what I find really interesting is developed independently from the buildings in North Africa. So this has come. The people have the same problem and they have come to the same sort of conclusion without talking to each other, basically. So turns out we're all very innovative and come up with the same sort of thing. So that's dense living. Right, living arrangements. So this normally is brought up in Britain, certainly, in the kitchens in houses are normally in the middle, and that the heat from the cooking heats the house, and that was historically what happened. Now that's happening less and less, but here this living arrangement, so this is in Ghana, is basically distributed living, and the way to think about this is think of outside as a room, and I think once you do that, it makes an awful lot of sense that that's a bedroom. That's a bedroom, this is the living area, and that's the cooking area, you see? So you don't want the heat generation, which is basically what we've got, in the sleeping areas, because you've got too much heat going on. So the answer there is move your kitchen, move your heat generation away from where you're sleeping. That's a living space layout point of view. And the opposite end of the spectrum, this is in Holland. So this is a sod house, very simple, very cheap. There's the chimney, and the cooking's right in the middle. So what you're trying to do there is get the maximum amount of heat in, and so it's not a great place to live, I presume. But at that end of the scale, you want to be putting the heat generation right in where you need it. So just two examples of either end of the spectrum. Where'd you put the kitchen? I think Pete Walker had this slide yesterday. So this is Kevin McCabe's house in Devon. From an engineering point of view, the walls only need to be so thick. There's no point making the walls any thicker than you need to from a structural point of view. And certainly historically, that's expensive. You know, that's really expensive if you're building your house. So I want to know why the walls are thicker in some places than others when they don't need to be. And some of this, again, might be lack of understanding. But I think the more I look into it, these people knew what they were doing. They knew exactly what they were doing, and maybe the explanations weren't quite right, but they knew what worked. And so here you've got additional thermal mass, which is required over the structural requirement, basically. And that really is just building yourself thicker walls. But from an earth building point of view, what you need is that thermal lag we talked about, I think was talked about earlier. So during the course of the day, wall heats up, and then wall heats up during the day, and then you get a transfer of heat from the wall back into the rooms through the night. That thermal lag, that needs to be the right amount of time. And if it's not the right amount of time, then the system doesn't work. So you can design wall thickness for that thermal lag to work. And again, we get the same sort of deal with humidity absorption as well, a humidity flywheel. Right, moving on to slightly more heat flow related things. So these are in Harran in Turkey. This is the old hot air rises approach. I think it's used very well. It's used here, which is good. But it's been used for a long time elsewhere. So there we are in Haran in Turkey, and here we are in Cameroon. Similar principle. Open at the top, lets the heat out, and a nice cool space inside. I presume. I'm not sure about that. Is that a cooking thing as well outside? So we've got the similar setup as we saw in Ghana of sleeping spaces that stay cooled, cooking spaces outside, and shade there as well. So whenever I give an earth building talk, we always talk about termites. People often show pictures of termite mounds, but I think these guys get, we need to, look at what they really are. These guys know what they're doing. The termite mound works through a stack effect, and heat is generated at the base, comes out the top. So, let's imitate nature and imitate the termites. Slightly differently, wind catchers. So a similar looking system, but I think I'd like to hear the talks that I think are not happening now, but the guys talking about the design of wind catchers. Takes a prevailing wind, takes cooler air in and fires it out, is my understanding of it. I'm very interested to know whether the wind catchers really are working like that, or whether they're just a different take on the stack effect. But I'm sure that can be, we can talk about that. But a very simple, easy to do principle, but that's expensive to build. That's difficult to build. You've got to be working quite hard to build a wind catcher onto your house. And 33.8 metres mud bricks. That's good going. I don't know what the highest one in Australia is, but they win. Right, next one is evaporative cooling. So this is in the Alhambra in Granada, in the southern part of Spain. Parts of it are rammed earth, parts of it are adobe, and parts of it are masonry. But the principles work the same. This was the centre of the Islamic Caliphate up to 1492. This was top end technology, and this was the best place to be, and the whole system there is around evaporative cooling, which is basically channel. This particular place is fountains, gravity-fed fountains. That's a fountain. The fountains comes out of the lion's mouths, and then it flows into these channels here, and then these channels distribute around the building. So there's evaporative cooling from there, and it just cools that space. It's within a courtyard with overhangs and cooling, and there we go, there's another example of it. The way we've got it is the release of the latent heat of vaporization. So we're taking energy out of the system. And to my mind, this is the best way to do it, because all you've got to do is supply water. Again, comes down to whether you've got a water supply. So just taking the technology a little bit further, this is an ice pit. So ice in the base there, evaporatively cools. You lose the latent heat of vaporization from ice to water, and then again from water to water vapor, and then comes out the top. So you get a very cool space in there. Another big civil engineering feat is these cats, which are underground canals across Iran, and they transport water from the mountains. They take in, they evaporate water into a cooler basement, and it comes out. You end up with a cool basement, but a big civil engineering project to transport water and keep people cool. There's a lot of thought and technology gone into that, and we need to steal that. I think that's my take on this. So I don't know how I'm doing for time. 6 minutes, amazing. Okay, so what I would really like to do is map this against the climate classification graphs. I really did. I started off and I thought, right, it's going to be quite straightforward, because we're going to have in the red zones here, let's say, we're going to have a one type, and then, oh, brilliant, we can use that here. Fantastic. It's more complicated than that, as I think's been discussed a lot of times. There's many variables. Which were talked about before coffee. I think what we need to do is be aware of all the principles, choose the correct ones, and then work with those, basically. So that's just a map of all the sites that I've talked about. I can't see a good, solid correlation on those. Anyone wanting to do a PhD or a master's student, I'd love to know, see if there is anything in that. So, right, in conclusion, no energy input, free running, definitely the best way to go. You can sort that out with building orientation, building height, building layout, architecture, for want of a better word. That's how you do your building design. Once you've done all of that, then you've got to add fuel. You've got to add energy to the system. You can do that through evaporative cooling, through fuel heating. It's not rocket science. You know, we can work it all out. What I would say is, don't reinvent the wheel. I think I've been to a number of these conferences, and the same things get talked about from conference to conference without any real resolution. So hopefully, I think this one, it feels like we're really moving forward. So that's good. And really, we do face exactly the same issues as historically. We've got the same thermal comfort possibilities. We have the same thermal comfort as people in the past. We just need to work with that. And energy to actively heat and cool is expensive. So, I mean, basically, don't waste it. That's the bottom line. But I would like to move on to, so this is a house that's for sale in Albury. Around the corner from here. I just went onto the real estate website and picked the next one. So presumably this has got all the brand new house. It must have the right thermal design, thermal rating. People will want to live there, but it's not really got any of the principles I think we've talked about. But it should. I think is probably the message from that. Next slide is free heating and cooling energy. So this, if you recognise that car, that's a Tesla car, and this is his solar cell roof tiles. The aim of the game is to get the price of those cheaper than regular roof tiles. Will the cost of energy production come down? And is that something to worry about or not? I think it's an interesting point. I think that's fine, but I think through architecture and through your building design, we still want to be minimising the energy use. You know, that's the bottom line. That's what we've got to work on. So I'll finish on challenge assumptions. I think my main takeaway from that is this is a mud brick wall. Round earth wall in Spain in the rain. It's been there 700 years. Seems to be doing all right. When we first arrived, we couldn't work out what was going on. I think it's probably stabilised with the pozzolan that Pete Walker was talking about. So we didn't know what was going on with that. Now we do. Improve your understanding. I very much feel that we need to, through more understanding, we're getting better. It's no good just saying, well, that's too complicated, can't do it. We can understand the complicated, simplify what can be simplified, and then sort it out. But don't throw the baby out with the bathwater. Improve your tools. I think the climate modelling and the building modelling software we've got at the moment. I think it's come across that there are a few issues with that, and it might need a bit of improvement. If we know how to do it, we can do it. We can sort that out. And I think the final thing to finish on that we're talking a lot about here is regulation follows innovation. So you've got to innovate first and then you regulate, not the other way around. If you regulate first to then force people to innovate, that doesn't tend to work very well. And I think just an example of that is British Standard 1, which is for railway sleepers and railway irons and steel. So people produce things. Then the railways started failing. That was bad. So the regulations came along to standardise sections. It's happened all the way through. Innovate first, then regulate. And that is where we're at with earth building and thermal design. So I think that's it.